Today we're going to introduce you to logs. And in order to do that, we're going to start by talking about these graphs right here. We have graphed y equals 3 to the x power. As we plug things in, and this is one you can put in the calculator and get the table, but we'll go ahead and plug in the values. So 3 to the negative 2 power gives you 1/9 because the negative exponent does the reciprocal. So if we got 3 to the negative 1 power, that would be 1/3. And then 3 to the 0 power, well, any number to the 0 power is 1. And then 3 to the first power is itself 3. And then 3 squared is 3 times 3, which is 9. When we graph this, it gives us the points at -2, 1/9, at -1, 1/3, 0, 1, 1, 3, and 2, 9. So we get something that gets really close to the x-axis, touches that point at 0, 1, and then starts to go up very quickly. We say it has a horizontal asymptote at the x-axis, so this is following along on the x-axis forever. It never touches the x-axis or goes into the negative side. So that's the exponential we've been working with for the last couple class periods. Now if we switch that x and that y, like we've done on this one here, then 1/9 in the place of the x would be 3 to the negative 2 power because that's the reciprocal there. This one's not one you can put in the calculator, so we're going to think through this one. If my y value was -1, that would give me this, which is 1/3. And so that would be the opposite table as this one. So this would be 1, this would be 3, and this would be 9. And so if we go ahead and graph that, and I'll go ahead and write these out. Whoops. 3 to the 1 and 3 squared. So you can see where those values came from. Now we're going to go ahead and graph the points that were just made on this table of value by switching that x and y. So if I graph 1/9 and -2, that's right there. And then 1/3 and -1, it's about right there. 1, 0, 3, 1, and 9, 2. We get a graph that looks like this. It's a reflection across that y equals x line. So our y equals x line was graphed already for us right there. But we see that that's a reflection across that line. And we've switched the x and y. So you should have a light bulb now because we've talked about what relationship that is before. That's an inverse relationship. When we switch our x and y, and it's a reflection across this y equals x line, that's the definition of an inverse. So we have just graphed the inverse of an exponential. The inverse of an exponential has a name. It's called a logarithm. So this is a log function, and we're going to get more into that. So our exponential here was y equals 3 to the x power. This log would be log base 3 of x. That's its inverse right there. And we'll get more into that as we move on through the lesson. But this one is an exponential, this one is a log, and they are inverses of each other. If we think about the domain and the range of this, for the exponential graph, we said the domain was all real numbers, or -infinity to infinity, because it went from all the way to the left and all the way to the right. If we think about its range, it starts at 0 and goes up forever. And we said that would be a parentheses on this side because it would not include that 0 point since it never touches the x-axis. Looking at our new graph, it is not touching the y-axis and moving to the right from that point. So our domain would be 0 to infinity. Again, not touching that y-axis, so this would be a parentheses, not a bracket. However, it goes all the way down into the negative y values. It hits the 0 y value, and then it goes up forever. So this one would be all real numbers, or from -infinity to infinity. Notice that they switched. Again, we know that from the definition of an inverse. The domain and the range switch because we've switched the x and the y. It asks us here, does each represent a function? Yes, they both pass the vertical line test, and so we know that those are both functions. Those are the functions for this unit, the exponential and the logarithm. All right, we're going to go a little bit deeper now with our exponentials and logs here. And so we're going to look at y equals 10 to the x. That is graphed right here. We've been working with this graph, so we know what that looks like. It follows the x-axis forever here, so we know that it's got a horizontal asymptote. All of our points are above the x-axis, so we know that our range starts at that 0 and goes up. It does go all the way to the left and all the way to the right, so we know our domain is all real numbers. So let's start filling some of this out. Our domain is all real numbers. Our range is from 0 to infinity. We know that the y-intercept for all exponentials is that 0.01 unless it's been transformed. So we've got that y-intercept at 0, 1. Our horizontal asymptote is y equals 0. It is a horizontal line, so we know it has to be y equals, and the value there is 0. For our end behavior, as x is approaching negative infinity, so on the left, y is approaching 0 because it's getting closer and closer to that 0 value there. On the right-hand side, as x approaches infinity, y is approaching infinity as well, since on the right-hand side, it is moving up forever. Now we're going to look at the log that's graphed here. So this is a log. It has no base written right here, so this is called the common log, and it has a base of 10. So these two right here are inverses of each other. When there is no number written there, it is a 10. So this is the common log with a base of 10. I'll go ahead and write that out to the side. That is a base of 10 when there is no number written there. So these two right here are inverses of each other, and we want to look at its graph. So on this one here, it is not touching the y-axis, even though it kind of looks like it. It is following it along forever as it goes down. It then hits this point here at 1, 0. That is our x-intercept. Notice that's the inverse point from the one that we had in the exponential. It then goes to the right as it goes up forever. So our domain starts at 0 and goes to infinity. And our range is all real numbers since it's coming from the bottom and going to the top. Again, the calculator can't graph a vertical line. So when it's getting closer and closer, it looks like it cuts off right about there. You need to know that logs continue down forever. It follows that y-axis forever. The pixels just don't allow you to see that on a calculator. For our, notice that's a VA, vertical asymptote. So we had a horizontal asymptote for the exponential. We've got a vertical asymptote for the logarithm. Vertical lines are x equals, so that should be an x equals and 0. It is a vertical line right here, the y-axis. I'm going to write that out to the side so you understand that's the equation of the y-axis, and this one is the equation of the x-axis. For the end behavior here, it is as x approaches 0. Since we know it does not go any further this way, it's as x approaches 0, y is approaching negative infinity. And as x approaches positive infinity, so on the right-hand side here, y is approaching positive infinity as well. Here's our basic attributes for exponentials and logs. It's important that we know these pieces so that when we transform them, we know where each of these pieces came from. So now we're going to go to the definition of a logarithm here, and it's written in math terms. So it says if b and x are positive numbers, b is unequal to 1 and x is greater than 0, then b to the y equals x if and only if log base b of x equals y. So what does that mean? I'm going to go ahead and write it in a form that you can understand better. And so we've got, and that's when we put these in kind of right on top of each other. So I've got by equals x. If I've got an exponential that looks like that, I can convert this to a log. The base on the exponential is going to be the base on the log. The exponent is then freed to become my answer, and the answer becomes my argument. That's what goes right here on a log. This is called an argument, and this is called a base. And so the y would be freed here. So our exponent becomes that result, or our answer. The answer here becomes the argument, the inside part of that log. You have to be able to know how to convert from an exponential to a log and a log to an exponential. That's going to help us when we get to solving. When we're solving for an exponent, we can use a log. By converting, then you're taking that exponent out. So we're going to practice a few. So we've got log base 3 of 9 is equal to 2. The base on the log is the base on the exponent, so I will have 3. And I like to do it right on top of each other so that I can see it drop and then switch. So that becomes 3 to the second power equals 9. This is an easy one to check since it's numbers and we know 3 squared is 9. Here's a second one. We drop it. The base on the log is the base on the exponent. The switch, so I get x to the third is equal to 8. And then for our last example here, we drop the 5 and switch those. We get 5 to the x power is 25. Sorry about that, you couldn't see that. So the base on the exponent is the base on the log. And then the other two switch. The same is true when you're going from an exponential to a log. We drop the base here, so we get a log with a base of 3. And then we switch the other two. So we get log base 3 of 81 is equal to 4. That's one you can also check on your calculator because it does have all of the values there, and we'll get to that on how to put it in the calculator. Actually, let me just show you right now. So on your calculator, you would hit alpha and window, and that takes us to this place here where it says log base. That allows you to put any log you want into the calculator. And so we'll put a log with a base of 3, and then 81, and that gives us 4, which is what we wrote here. We're going to use that alpha window anytime that you have a base written. You want to go to that log base right there, alpha window log base. If it does not have a base written, so that common log, it does have a button by itself to the left of the 7. When you hit this log button, it is assuming that base of 10. You'll see that right on top too if you forget that 10 to the x, the inverse is written right on top. So this log is a base of 10. There is one next to the 4 as well. This one right here is called the natural log, and it has a log of e, which we will get to further on in the unit. All right, so practicing this log, we drop that 3, so we get a log with a base of 3, and then we switch, so we get 5 is equal to x. Log base 3 of 5 is equal to x. And then again here we drop that log base e. This switches, 7 is equal to x. And that right there is that natural log, which we'll get back to later. So we get a log base e of 7 is equal to x. Again, you have to be able to convert from a log to an exponential and from an exponential to a log. So make sure that you can use that definition that was given here, and we just wrote out this way. We're going to use that definition to be able to write the inverse of these functions. So we're going to rewrite the inverse of the exponential. If I wanted to write the equation of the inverse of this, so previously we learned the first thing we do is switch the x and the y. So we get x is equal to 2y to the third power. I'm sorry, 2 to the y power plus 3. Said that incorrectly. X equals 2 to the y power plus 3. That's my first step. I've switched my x and y. Now I want to get the y by itself because we never leave y inside the equation since that's our dependent variable. So I'm going to subtract the 3 to get it to the other side. That gives us x minus 3 is equal to 2 to the y power. This is where we're kind of stuck because now the y is in the exponent. And so previously we didn't know how to get this out of the exponent. This is where we want to convert it to a log so that we can free that y. The base on the exponent becomes the base on the log. So that's going to drop down. We get log base 2. And then they switch places. So this x minus 3 is my argument and the y is freed. So this right here would be the inverse of 2 to the x plus 3. You want to be very careful where that 3 is. So I'm going to do a side note here just to make sure that you guys see another one. If this was in this format here, y is equal to 2 to the x plus 3 power, the first thing we do is switch our x and our y. And now we need to free this exponent. We cannot subtract 3 at this point because all of this is in the exponent. So to free all of that, we drop the 2, so we get a base of 2, log base 2, and then they switch. So we get log base 2 of x is equal to y plus 3. Now is when you would subtract that 3 to get it to the other side, so we could leave the y by itself. And here's the tricky part. This x is already in the argument. This is all one term. So we are subtracting 3 from that at the end there. This is not the argument. That negative 3 is on the outside part. All of this part is one term. In this case, all of this is one term because we have this parentheses and this entire x minus 3 became the argument. So these two are different. Make sure that you're following the proper order of operations. All right, so now we're going to write the inverse of a log so you can see how that works. Again, to find the inverse, our first step is always to switch the x and the y. So we do that first. Now it's time to get the y by itself. Well, all of this is in the argument, so we cannot release it since all of this is one term. The only way of getting this out of the argument is to convert it to an exponential. So that's what we do. We drop the 4, and then we switch. This x becomes my exponent, and the y minus 5 is freed. Now we're able to get the y by itself by getting rid of this minus 5, so I add 5. We get y is equal to 4 to the x plus 5. That's the inverse of that log. As we practice evaluating some of these, we will do some on the calculator and we'll do some without the calculator. You should be able to do both. If there's something like this, log base 4 of 64, in order to evaluate this one, we can set it equal to x since that's the unknown, what value is. And then I can change it using the definition to be 4 to the x equals 64. Well, 4 to the third power gives us 64, so we know x is 3. Here's another one we can do without a calculator. We drop the base of 2, and then we switch, so we get 2 to the third is equal to x. Well, 2 to the third power is 8, so we know that's our x value. Here's some that are a little bit harder. You can do them with both the calculator and the without a calculator. We'll practice the C with a calculator just so you know how to get this in. Again, we do alpha window, and we want to go to our log base. That's going to allow us to put whichever base we want here. So we want 2, and then in the argument, that's the part inside the parentheses, we want a 32. Sorry about that. There is a glare there. So we got log base 2 of 32. We hit enter, and that is 5. And so then we would get 5 is equal to 3x. And so we divide by 3. Here's another one. Now, this cannot be put in the calculator the way it is. So we would drop the base, and we get x to the negative 2 power is equal to 1 over 9. Since this is a variable, it's not a number, we're going to have to figure this one out without the calculator. So it's got a negative 2 power. We know for a negative power, we do the reciprocal. So this would be 1 over x squared is equal to 1 over 9, which means that x squared has to be equal to 9. And 3 squared is what is 9. So you should be able to evaluate some of these basic ones using that definition to convert back and forth between a log and an exponential. And a lot of times that means you can go ahead and plug it into the calculator once you've switched it. Like this one here. We switched it. You could have then put that in the calculator. When it's like this, you can go ahead and put that in the calculator since there's no variables in the base and the argument.